Hey everyone, today we are going to finish section 7.5. It's the same standards as what we looked at in the last video, only in this case we're going to put it into a word problem context, which will lead us very nicely into section 7.6 in the next couple days. So we're going to be looking here at rates of change, most of which are going to be related to time. And it's important to note that in real life, there are lots of quantities that vary with time, and calculus helps us to make sense of those quantities. So for example, temperature varies continuously. Sometimes the temperature increases, sometimes it decreases, but as time goes past, the temperature is changing. The same for height of the tree. As time goes past, the tree is going to be getting taller. Stocks and bonds, shares of various companies go up and down, their prices increase and decrease, and we can model those quantities using functions of time. And what we're going to talk about is how to look at the units on those types of things. So for example, S of t in mathematics, S of t always measures distance. In this case, S of t is going to be the distance traveled by a runner. Well, if we do that, then the derivative, ds dt, or s prime of t, is the instantaneous speed of that particular runner. How fast is the runner going exactly at 3 seconds, or exactly at 2.57 seconds? So look at what we have here. Speed is in the numerator, distance is in the numerator, time is in the denominator, so the speed, which is this whole thing, could possibly be measured in meters per second. And remember, if you wanted to, you could write this as meters per second. That little -1 puts it down in the denominator. So you can see that the distance is going in the numerator and the time is going in the denominator, giving us a rate quantity, meters per second. Okay, same idea here on the next one. H of t models the height above the ground of a person riding in a Ferris wheel. Well, if we take the derivative of that, then what we're going to get is the instantaneous rate of ascent of the person in the Ferris wheel. So if our rate turns out to be negative, that's a negative rate of ascent, or basically a descent. The person is going down. So again, possible units, I'm going to put the height in the numerator, the time in the denominator, and I end up with meters per second. Or it could be, depending on the Ferris wheel, meters per minute. It could be any kind of unit that you need there. Meters per second just happens to make the most sense in this particular case. Okay, so let's look at this one. The volume of air in a hot air balloon t minutes after taking off is modeled by this particular function, and that function is valid from 0 is less than t is less than 8. So basically the first 8 minutes of the hot air balloon ride, the volume is going to be given here. All right, so the initial volume of air in the balloon. So think about what that means. The initial volume, initial meaning at the beginning. So when we first start filling up the balloon, we're getting ready for our hot air balloon ride. We're going to fill up the balloon. Well, that means that 0 time has passed. At the very beginning, we haven't put any air in there yet. So now let's see what happens. I'm going to put 0 in place of all the t's. And if I figure this out, 0, 0, 0 plus 2 is going to be 2. Okay, so think about what the units are going to be here. In this case, notice that I'm not finding the derivative. I'm just using V for volume. So the units, they're going to give me those right here, are going to be meters to the third. All right, let's do the same thing when t equals 8 minutes. So 8 minutes have gone past in our filling up of the balloon so that we can take our balloon ride. So I'm going to put 8 in place of all the t's. That's a terrible looking 8. All right, and I went ahead and typed this in my calculator, save us a little bit of time. That's 914 meters cubed. So you can see that there is much more, the volume is much greater here than it was here, but the units are staying the same. In both of these cases, I'm measuring volume, so I've got meters cubed on both of them. Okay, part C, find dv dt. So that's asking us to take the derivative. So I'm going to take the derivative of v up here at the top. So 2 times 3 is 6. 2 times 3 again is 6. And I'm going to multiply 1 times 10, and I'm going to end up with that. So find the rate of increase in volume when t equals 4 minutes. So exactly at the instant when I'm at 4 minutes, how is the volume of air in the hot air balloon changing? Well, in this case, I'm going to plug 4 into the derivative, not the original. All right, let me type that one into my calculator real quick. And you get 82. Okay, now let's think about what the units are going to be here. So I've got dV dt, the volume goes in the numerator, and the time, which in this case is minutes, goes in the denominator. So the rate of change is 82 meters cubed per minute. It becomes a rate instead of just a volume when we take the derivative. All right, so some things that you need to write down. Take a few minutes, pause the screen, write these things down. This idea of C of X and P of X and R of X is really useful not only in calculus, but if any of you guys go into a business application, if you take a business calculus or a business pre-cal class in college, you're going to do a lot of things with these particular equations. So take a minute, pause the video, and write these things down. Then we'll talk. Okay, so in this case, C of X is the cost of manufacturing. That makes sense, C for cost. And the derivative is the instantaneous rate of change in cost with respect to the number of items made. So what is the rate of change of cost as you are making the 27th item of this particular thing, or as you are making the 357,000th item of this particular thing? So an economist would want to know, how is the cost changing as I manufacture fewer or more items? So this would be a very important thing to know in a marketing sort of idea, in a cost analysis sort of idea. All right, so think about what the units are going to be there. dC dx, the cost of manufacturing, and then x was the number of items. So in this case, we're going to get dollars, cost is measured in dollars or whatever the currency is of the particular country, in case you get an international question, per item, because the X in the denominator is the things that you're making. So dollars per item. All right, now think about profit. Profit is how much money you get after you have your revenue, how much money you bring in, and you subtract away the cost that you have. So for example, if you have a lemonade stand and it costs you $7 to buy the ingredients for the lemonade, that's going to go here, $7 for cost, and you make $12, that goes here. 12 minus 7 is 5. Your profit is actually $5, not $12, because you have to take away how much you spent on ingredients. All right, if we take the derivative, rate of change of profit with respect to the number of items sold, and again, we're going to use those same units for that, dollars per item, or whatever the value of the currency is in that particular country per item, is going to be that same unit, no matter if you have dpdx, drdx, or dcdx, they're all going to be that same unit. Okay, let's look at this one. So suppose that we are producing items in our factory. The cost is here. Okay, now just as an FYI, the way this is set up, these are your labor costs, your raw material costs, and then your fixed costs. So if you were going to go into an economic sort of major, that would be important. For the purposes of IB, for the purposes of this test, it's not important, but just so you know what you're looking at here. Okay, so it asks us to find C prime of X. Okay, so let's take the derivative. It's a little bit tricky with all of these long decimals, but you work it the same way. 0, 0, 0, 13 times 3, 39, x squared. 0, 0, 0, 4, because it's 2 times 2, plus 5. Okay, so now it asks us to find C prime of 150. Okay, so that means I'm going to substitute 150 for all my x's. Put 150 right there. All right, and I'm going to round this one. I already typed it in. So this one is going to round to 14.88. Again, sorry, it's really hard to make 8s on this. All right, now think about what the units would be there. This is the derivative of the cost function. Cost is in dollars, and it's dollars per item. So I'm not going to put a dollar sign here because I'm not just finding the cost. I'm finding the dollars per item. I'm finding the rate of change of the cost. Okay, so interpret this result. What does this result actually mean? What it means is that because I got a positive number here, that the cost is increasing at the 150th item. So my rate of change is positive, meaning my cost is increasing. Okay, if I were going to do this one, C of 151 minus C of 150. All right, notice here I do not have any primes. I'm not doing the derivative. I'm just substituting into the original function up here. So I will take 151, 0, 3, and put it in there. All right, now I want to subtract and be really careful doing this kind in your calculator. You want to make sure you have parentheses on this whole thing so that you subtract all of it. The biggest mistake I see here is that people forget the parentheses and therefore they actually only subtract part of it on accident. Okay, so I will type all of that in my calculator, which again I've already done, and this works out to be approximately 14.44. Okay, so again, think about what the units are going to be there. In this case, I've just got C. I don't have C prime. So what I've actually found is just the cost in dollars. So $14.44. All right, so what does that actually mean? That actually means the cost of producing the 151st item is $14.44. It's changing at this rate, but actually it is this rate, it's this much at that moment. Okay, at this point you can finish your worksheet from section 7.5. Be sure to upload a picture of that, and we will get together on Friday and talk about the answers.